Hello again, organickers. Um, I wanted to talk to you. I cut the last video short a little bit because I wanted to talk about um, constitutional isomerism in some detail. Even though it's a couple of slides in the presentation, you really have to understand how to be able to analyze structures and to look and make sure if one is equivalent to the other or if it's just a rotation about a bond that causes something to be different. So here I have butane, which is the 4-carbon. I have 1, 2, 3, 4. This 4-carbon chain is going to be butane in the staggered form, right? And you can see it has CH3, then it's got CH2, then it's got CH2, then it's got CH3. This is the same compound regardless of how I rotate. I could have it in this orientation, and just by rotating, right, I could draw it a multiple of ways. So on paper, I could draw it so it looks like this. It would still be exactly the same compound as this, which would still be the same compound as that staggered form. So you have to be able to use your models. This is why models are so critical. You can build these compounds and then you can look at them, and just by rotating bonds you can determine if something is the same or something is different based on looking in it in 3 dimensionals, which is what the modeling is good for. So let me continue on with what we were talking about. And what I have here is going to be where we left off. Remember, these are straight chain. These are straight chain linear compounds that are described here, which means they just go end to end to end to end. So this prefix is telling me the number of carbons. So remember, meth means I have 1 carbon. Pent means I have 5 carbons. So this is how I have a condensed structure. I have 1 carbon, 3 times 1. That means I have 3 carbons in this little branch, or this little piece here, and then I have another carbon. So I have 5 total carbons. If I want to look at that in terms of the angle or the line angle, it would just be 1, 2, 3, 1, 2, 3, 4, 5. So this is equivalent to pentane, just like this one was equivalent to octane. So again, this is condensed, and then this is line angle. And I like the line angle. Line angle is going to be what we use a lot in this class. So you have to be able to draw structures based on the connectivity of the carbons and the hydrogens. Now, there's something about alkanes called constitutional isomerism. In that chart, those were all normal or linear, where each carbon is just connected to another carbon sort of staggered. So linear would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and I just keep on going that way. Branched is where maybe instead of just having my hydrogens on any one of these points, I actually have another carbon. So if I put a carbon there, now I have 5 total carbons, 1, 2, 3, 4, 5, but I have a branch here. So this carbon is going to be my branching point. So here I have linear, and here I have branched. Notice I still want to look at, this one has 1, 2, 3, 4, 5, 6, 7, 8, 9. So this has 9 carbons, C9H20. This one has C9H20. This is an isomer of this, right? So you can imagine, as I add branching, the number of isomers that are possible grows really, really quickly. So if you think about it, here's my molecular formula. This does not tell me if things are connected in a straight chain or if I have branching. For methane, I can only draw one isomer. For ethane, I can only draw one isomer. For propane, I can only draw one isomer. But here's where it gets interesting. Once I get to 4 carbons and higher, now the connectivity can be different. I could have a 4 carbon linear, 1, 2, 3, 4, or I could have 3 carbons in a line and my 4th carbon branching off of that central carbon. Those 2 molecules are constitutional isomers. They both have the formula C4H10, but their connectivity in space is different. Let's look at C5. I could have linear 1, 2, 3, 4, 5. That would be just pentane. I have a linear system. All 5 of my carbons are connected to one another in a straight chain. Or I can branch. I could have 1, 2, 3, 4, and maybe I have a branch there. Notice that if I put my branch here, those are equivalent compounds. I have a carbon, or I have a carbon, then I have a branch, then I have a carbon with CH2, I have a carbon with CH3. Here I have a carbon branch, carbon with CH2, carbon with CH3. Those are equivalent structures, even though they might look different, because they have the same connectivity. If you drew a model and you put those together, what you're going to notice is I can sort of draw them in any which way. I'm going to go ahead and stop the share. And I want you guys to look here. Here's my 4 carbon chain, right? This is 4 carbons. If I add a 5th carbon, I'm just going to add this. And now here's my pentane. 1, 2, 3, 4, 5. So that's my linear pentane chain. But now let's make a branch. What if I do this? I'm going to take my whole carbon and I'm going to reconfigure. So now I still have 5 carbons, but now I have a branching point. Now notice I could have carbon CH3, carbon with a carbon CH3, and this hydrogen back here, CH2, CH3. And I could draw that on paper, or I could just flip it this way, and now it's reversed. Or I could flip it this way, or I could draw it this way, right? This is why making a model is really important. I have to be able to take what's written on a piece of paper and figure out if they're the same or if they're different. They're going to be different if they have different connectivity. They're going to be the same if I have the same connectivity. So here is my 5 carbon that has a branch, and I can draw it many different ways. I can flip things around, and that can be translated on a piece of paper in my line angle formula. And it can be drawn multiple ways. Pretty much the convention is I'm drawing my largest chain staggered with my branching points coming off, but it doesn't have to be drawn that way, in which case you have to get really good at figuring out if something the same or if something is different. And that's the whole idea with constitutional isomerism. So when I look at these, I have to be able to, again, if I have that 5th carbon, right, if I looked at this, I could draw it 1, 2, 3, 4, and that would be the same thing as that. I could draw it 1, 2, 3, and have the branch. That would be the same as that. It doesn't matter how it's drawn. What I have to do is figure out connectivity. So I have carbon, carbon with another carbon, carbon with a CH2, carbon with a CH3. I have carbon, carbon with another carbon, carbon with a CH2, carbon with a CH3. I have carbon, carbon with another carbon, carbon with a CH2, carbon with a CH3. So this is what you have to decide. You have to figure out if something is going to be the same or if it's going to be different. If I have the same connectivity, it will be the same compound. If I have the same molecular formula, but I have different connectivity, then it's going to be a constitutional isomer. So what you have to do is be able to recognize different structures as either being isomers or being the same compound. So if I have all of these different things here on my slide, this one is 1, 2, 3, 4, 5, 6. I have 6 carbons. It's in a straight chain. So 1, 2, 3, 4, 5, 6. It doesn't matter if I go ahead and I number from the other end. 1, 2, 3, 4, 5, 6. I know that I have 6 carbons connected in a straight chain. Here, I have carbon number 1, carbon number 2, connected. This is a branch. 3, 4, 5. This has 6 carbons total, but I have 5 carbons staggered, and then I have a 1 carbon branch. So this and this are different. They're not the same, right? Here I have 1, 2, 3, 4, 5 with my 6 carbon. I have 6 carbon total. I have 5 carbons connected with a 1 carbon branch. But notice this branch is on that central carbon. This branch is on the carbon that's on the 2nd carbon from the left. This branch is on the carbon that's on the 3rd carbon from the left. So these two are not equivalent. 1, 2, 3, 4, 5, 6. 6 carbons total, 4 in a straight chain, 2 1 carbon branches, right? So here's a branch, here's a branch. And then this would be my longest chain there, right? 1, 2, 3, 4. I have a 1 carbon branch, a 1 carbon branch. 6 carbon total. I have 4 connected. I have 2 1 carbon branches, but both of these branches are on my second carbon. 1 branch here is on my second carbon, 1 branch there is on my third carbon. So these are not the same. These are not the same. So let's look at this last one. I have 1, 2, 3, 4, 5 with a branch off of carbon 3. That's the same thing as this one. So those two are identical structures. The other ones are all constitutional isomers of one another. Now, the best way to make sure that you know what you're doing is to build a model. You can flip the structures in 3-dimensional space. You can rotate it around its single bonds until it's superimposable on the other molecule. So the best way to do this is going to build the model and rotate things, see if they're the same or if they're different. You want to pay attention to the connectivity. What carbon? Are they connected on the same carbons? But recognize the carbons can be flipped around, right? I can rotate it by 180 degrees, right? I can rotate it any way I want to. So let's go back to the thumbnail, right? Remember, here's my 4 carbon with the 1 branch. But if I want to figure out, I could write it this way, right? I'd still have 1, 2 with a branch. I could draw it this way. I could draw it this way. I could look at it this way, or this way, or this way, or this way. What you have to do is look at the connectivity. Carbon with 3 hydrogens connected to a carbon with 2 hydrogens, connected to a carbon that has 1 hydrogen and a methyl group, right? Connected to a carbon that has 3 hydrogens. You need to make your models in the beginning to be really sure about what it is that you're actually looking at in terms of constitutional isomers. All of these bonds rotate. Everything is rotating, right? All of my sigma bonds can rotate. So what I have to do is make sure that what's written on the paper in 2 dimensions, I have to be able to picture it in 3 dimensions, and then I have to be able to see if what is drawn in the molecular model, right? If what's drawn in 2 dimensions is the same or different. If I have the same molecular formula and it's the same connectivity, it's the identical structure. If I have the same molecular formula and the connectivity of the atoms is different, I have branching, or my branching is on different carbons, those are going to be constitutional isomers. You got to play with your models. You got to practice this. If you get this down good right now, this will be really important, because as we go forward, you have to know what these structures look like, and you have to be able to recognize sort of equivalencies in terms of the structures from one structure to another on paper and in 3 dimensions. Okay, next time we talk, we're going to be talking about how I name alkanes.